You know, some questions in math seem to have one single, perfect answer. The kind of thing you learn once and it just sticks with you forever. Well, today we're going to look at one of those classic questions, and we're going to watch as that one perfect answer completely explodes into an infinity of truths. Let's get into it.
So here it is, the fundamental question. For thousands of years, mathematicians have known that prime numbers, the ones only divisible by 1 in themselves, just keep on going forever. But how do they actually know that? The answer has been a cornerstone of math for, well, a very long time.
Yeah, for over 2 millennia, if you asked a mathematician for the proof, they'd give you one name: Euclid. His argument was so clean, so elegant, so complete that everyone just considered it the final word on the matter. Problem solved, case closed.
So that's it, right? We're done? Well, not quite. To really get what's going on, we first have to understand the genius of Euclid's original argument and see why it was considered so perfect for so long.
Euclid used this brilliant technique called proof by contradiction. And the idea is actually, beautifully simple. You start by assuming the exact opposite of what you want to prove is true. Then, if that assumption leads you down a path to something that's logically impossible, a total contradiction, well then, your first assumption must have been wrong all along. It's like setting a perfect logical trap.
Okay, so here's how Euclid sprang his trap. First he said, all right, let's just pretend the list of primes is finite. Let's say we have every single one of them right here. Step 2, he creates a new number, let's call it n, by multiplying all of those primes on his list together, and then just adding 1. And this is where the magic happens, the paradox. This new number, n, it has to be divisible by some prime number, right? But wait, when you try to divide n by any of the primes on your supposedly complete list, you always get a remainder of 1. That's a flat-out contradiction. It can't happen. Which means the only thing that could be wrong was that first assumption. The list isn't finite. The primes must be infinite.
It's just so elegant. It's undeniable. A single, perfect proof that stood unchallenged for 2,300 years. And it really feels like that should be the end of the story. But this is where things get really interesting. What if that one perfect proof wasn't just one proof at all? What if it was actually the doorway to an entire family of proofs, an infinite family? Okay, so check this out. The source paper for all this, by Ash and Peterson, introduces a stunningly simple little twist. They take Euclid's formula, and they add just one little thing, a multiplier, k. And here's the kicker. K can be any positive whole number you can possibly imagine. So let's see how this plays out. If you set k equal to 1, what happens? Well, the formula just becomes Euclid's original equation. It's the classic proof we just walked through. Nothing new there.
But what happens if we change k to 2? The logic holds up perfectly. We construct a new number, n, that's twice the product of all our primes plus 1. But when you divide this new n by any prime on our finite list, you still get a remainder of 1. The same contradiction pops up, but we got there using a completely different number. This is a genuinely distinct proof.
And we can just keep going. Set k to 1,000,000, 1,000,000,000, whatever positive integer you want. Every single time you generate a new number n, and every single time you arrive at the same logical dead end through a unique path. We've just turned one proof into an infinite number of proofs.
And this isn't just my interpretation. The authors of the paper stated directly, for every single positive integer k, we have a different valid proof. So we've just discovered our first infinity of proofs. But hold on, because it turns out there are different sizes of infinity.
Yeah, the story gets even bigger. We're about to make a jump from one kind of infinity to another one, a much larger one.
So the infinity we just found, one proof for each whole number k, is what's called a countable infinity. You can imagine lining them up and counting them off one by one, even if you'd be counting forever. But there's a bigger, denser kind of infinity called uncountable. Think about all the decimal numbers between 0 and 1. You can't list them because between any two you pick, there's always another one. It's a whole different level of infinity. So the question is, could there be an uncountably infinite number of proofs? To find this bigger infinity, we need a new tool. This is a famous formula from another giant of mathematics, Euler. Now, don't worry, we're not going to get lost in the weeds here, but the key thing to know is that one side of this equation involves multiplying all the prime numbers, and the other side is an infinite sum. And this formula sets up another impossible conflict. See, if you assume the primes are finite, that product of primes side of the equation gives you a nice, clean, rational number. But the infinite sum side, it produces an irrational number, like pi, a decimal that goes on forever without repeating. A single number can't be both rational and irrational at the same time. It's impossible. So boom, there's another perfect contradiction and another proof that the primes must be infinite.
And here is the absolute masterstroke. There's a variable s in Euler's formula that can be set to any real number between 0 and 1, not just whole numbers. We're talking 0.1, 0.11, 0.111, all the numbers in between. And since there's an uncountably infinite number of real numbers in that tiny range, we have just unlocked an uncountably infinite family of proofs, a fundamentally bigger infinity of truth. At this point, it's pretty clear we're not just finding proofs anymore. We're learning how to build them. It's like we have the blueprints for a mathematical proof factory. I mean, look at this. The source paper shows how you can basically set up an assembly line. You start with a basic recursive formula, then you can slot in a variable k to get that countable infinity of proofs we saw with Euclid's. But why stop there? You can add another variable, L. Or you can even replace variables with entire functions. You can use whole sequences of variables. Every new component you add to the machine creates another, often even larger, infinite family of proofs.
We've completely shifted our perspective. We've gone from admiring a single, beautiful, finished sculpture to basically owning the entire quarry and having all the chisels to make whatever we want. It's a method of endless creation.
But this explosion of proofs, it forces us to take a step back and ask a much more fundamental question. A question that's really less about math and more about philosophy.
The authors themselves bring this up. They ask, what really makes one proof distinct from another? When we change our k from 1,000,000 to 1,000,001, are we actually making a new discovery? Or are we just turning a crank on a machine we've already built? Where do you draw the line between a simple variation and a truly novel insight?
And that is the real takeaway here. We started with one of the most settled, solid truths in all of mathematics and found that it contains these layers of infinite complexity. And it leaves us with this final, fascinating question that goes way beyond prime numbers. In any field of knowledge, how different does a discovery really need to be considered truly different?